So checking to see if one of you could, I'm kindly asking one of you to confirm if you can hear me just fine. I certainly know you can see my screen because thank you for the thumbs up, because I have I have Google Meet activated on my mobile device, so I can literally easily check here. I want to start off, guys, I want to start off with an announcement already made, just a reminder though, that next week I'll be working from out of town. I think I mentioned this, and because of that, I'm going to have to suggest that we schedule interactions after 17. I apologize. It's just going to be on Wednesday, Thursday, and Friday this coming week. I hope I make it in time on Friday because so Wednesday. No, it's fine. I was thinking I was going to be traveling on. On Friday, but I'll be traveling back on Saturday. So please take note that the interactions on Wednesday, Thursday, and Friday are going to be virtual because I'll be working from out of town. I will not be in Osaka. And again, I imagine the two course reps have explained why we're having a virtual interaction today. Apparently, our venue SLH has a problem in terms of power here. Apparently, the power outlets or the sockets are non-functional, and because most of the things we are discussing require that you actually see what I'm talking about, I thought using the venue by scribbling on the whiteboard was probably not going to be fair on you, so we just resolved to having a virtual interaction. Incidentally, I'd asked around to see if we could find an alternative venue, and the only slot I could find for a venue was for 13 hours, and I'm told you have another class at 13 hours. But I'm gonna do a quick recap of what we did. Right, we did quite a bit here. We introduced this notion of perception and reality. I think in the other lecture, actually not last time, and then we decomposed. Right, we had a discussion about this. A discussion centered around the Polygon mesh, ideally, which is quite crucial to the things that we're going to be doing here. Specifically, we discussed the key components that comprise of this Polygon mesh, your vertices or your vertex, an edge and a face. Here's to hoping that we all understand what this is all about, is it? So the idea is simple. If you look at this excerpt or this image from our polyfield case example game, we see that we can actually represent this soldier using a polygon mesh, right? We also highlighted that the atomic unit is the so-called triangle, ideally, right? If you remember, and we realize that there's a reason why your so-called is it triangle is used in preference to other shapes. I don't know how much of this you remember, but we introduced this notion of planarity. So this idea that if we were to use another shape other than a triangle, like a more complex shape, for instance a polygon, what you have is a sort of situation where it will be difficult to represent it on a flat plane, right? Especially if you take into account the z-coordinate. So irrespective of the orientation of the triangle, the idea is you can pretty much be represented on a flat surface, ideally, right? So hopefully this is kind of like making sense, right? The triangle is always going to be flat, irrespective of how you want to represent it, right? It will always be flat in this case. And then we also indicated that the other reason why the triangle is used as the atomic unit is because of its simplicity. So in essence, any sort of complex shape you can think of. In fact, if you were to look at all these different interconnected dots here, at least the ones that are on the edges, as a single shape, you begin to realize that it's very easy and intuitive to actually break it apart or decompose it down to individual triangles. This would actually be difficult if we're looking at using a completely different shape. And then more importantly, there's a hardware part of things. So it turns out that hardware components like your graphics processing unit are optimized to process triangles mathematically. Okay, so there you go. 3 main reasons why we would be using why the triangle is used as the atomic unit ideally. And then we had a discussion of these key components comprising your mesh. I also preempted a discussion or a lecture we're going to have when we start looking at how we're going to be using, Python to represent these vertices, right? Or the matrices that we're going to be manipulating ideally. I just gave an example of how we would create a 2-dimensional array here using NumPy. You probably want to start kind of practicing as soon as you can actually, so that when we are cruising through this next week, you won't get lost here. And to help you out, I don't know if I did this, but I had mentioned that I'm using this current environment. I mean, if it changes, I'll probably share these details again. So these are various versions of the packages that I'm going to be using to demonstrate what will be done here. Just in case you need you want to make sure that you are executing the same exact code that I'll be using as examples in the course. I will share the requirements.txt file on the Moodle in case you want to in case you want to set up or we want to install or configure your system in the same way I've done ideally. And by the way, I'm using environments, right? Python environments ideally. I also hinted at the fact that when we start interacting with the OpenGL API, specifically using Py OpenGL, these are some sort of things we're going to be doing. And incidentally, in case you're wondering how a comprehensive code would look like, it's something like this, right? I guess the important things here would be the import statements, and then you initializing Pygame, right? Because you're using Pygame for windowing, and then afterwards you actually start drawing your triangles, your lines, or your points if you want to. So quite a basic process. We'll discuss this next week, but our goal will be to be able to, I don't know why this is not running here, but our goal will be to be able to do something like this, right? Draw your triangle, right? This thing here. Simple right now, but we'll try and see if we can get to a stage where we're doing more complex things than this. So anyway, so we mentioned this, and another important point here is as you are reading up, as you are researching on your own, just be mindful of the fact that early on in the process we're going to be using a legacy mode of OpenGL. If you're not using legacy mode, it turns out that the code that you tend to use is slightly different ideally. So the idea is if you were to run the code on the left, you'd get back an output like this, something that's very simple, but it allows you, notice here that the OpenGL API, after defining 3 vertices, allows you to draw your triangle, right? We explained or outlined what a vertex is ideally. We outlined the fundamental difference between a vertex and an edge, and also a face. The key things here to remember are that an edge comprises of 2 vertices, right? So 2 points ideally. It's a solid line that connects 2 points on your XY plane or something, and then your face is nothing more than just the skin, right? Again, your face would be made up of 3 vertices. Okay. I also hinted at the fact that when you are playing around with OpenGL and you want to draw something on the screen, will mostly be drawing points, so that's geo underbar points, lines, right? Your edge is your vertex, geo underscore lines, and your triangles. This is geo underscore triangles. Okay. All right. And then we briefly spoke about the coordinate system. Reminding ourselves first that the Cartesian plane that we are probably very familiar with from your, I don't know if it's primary school or something, typically would have your 0,0 on the bottom left corner, right, of your screen, for instance. And then positive y would be the direction going up, positive x would be the direction going right, whereas the screen coordinate system is slightly different. So 0,0 or your starting point, your initialization point will actually be on the top left corner, right? So positive is right for the x-axis, positive is down for the y-axis. Yeah, just take note of that. And then we also made mention of the fact that at some point we shall introduce this important concept of normalized device coordinates. So the idea here is we want to be able to standardize these different things that we're drawing on the screen, right? And the idea behind the normalized device coordinates would actually be working towards doing all sorts of projections to be able to reduce everything to lie between the range -1 all the way -1.0 all the way up to +1.0, right, or 1.0 ideally. And then I think we ended at a point where we're trying to remind ourselves that in as much as we're working with graphics, remember your computer architecture, there was mention of the fact that everything that is processed by a computer is actually perceived as ones and zeros. As human beings, it's not very intuitive for us to work with binary numbers, and so what we do is we abstract this idea of ones and zeros. In fact, they told us that what the computer deals with is not really ones and zeros per se, but electric signals. So when you're typing on a keyboard, that's an electric signal that is sent over as input to the CPU or something, and those things can actually be coded into a series or a stream of ones and zeros, right? So in terms of text, if you remember, they told you that one of the simplest things you can do is you can use your ASCII table, which will provide you with a predefined mapping of the different sort of characters you'd be working with. So think of the keyboard, right? On your keyboard, you'd have numbers and also alphabetical letters, right? Because we use English alphabet in our case. So you of course, there are also special characters here. So you'd have numbers or symbols from 1, or rather what we call 0, all the way up to 9. And what we were told is that in actual fact, behind the scenes, these different symbols can be mapped onto the equivalent number. So in this particular case, we see here that these characters here. I'm looking at it looks like my ASCII table doesn't have what I'm looking for here, but the space, there we go. The 0, right, is actually not converted to the binary equivalent. Okay. The binary equivalent of 0, like if you're using 8-bit representation, we're not saying that 0 is going to be mapped onto a stream of or a stream of 8 zeros per se, but rather, are you able to, Mr. Useko or something, are you able to, I don't know if it's Useko.
This shows the stuff, Mr. Dent. Why you've been hiding?
Yeah, I don't know about that. You probably mute your microphones or something like that. So if you look at your ASCII table, right, what we know as 0 is actually mapped onto it's mapped onto the hex 30 or decimal number 48, right? You can do your math if you want to. You can probably do a repeated division by 2 for this is it 48 here, so that you have the equivalent 8-bit representation of your binary number that represents 0. Or if you have some fancy calculator like I do here, I could just say what is a decimal notation, equivalent notation of 48 when converted to binary, right? And so the number 0 is in fact the number 0 on your keyboard is like, in fact, if you're using ASCII, represented as this, and the 0B here is just the way the application works. Now, because we're using 8-bit representation, it's like 2, 4, 6, so you have the 0, 0 here, right? So every time I type a 0 on my keyboard, we were told that, in fact, behind the scenes, it's codified back to this, right? Your A, would be the hex equivalent, which is, well, hex number 41 or decimal number 65. So again, if I was to use my calculator here, I'll just go to decimal 65 and just get the equivalent bit representation, right? The key here is the number of bits that you are using to represent. So in this particular case, again, I'll just have to make sure this is 8-bit representation. I have 2, 3, 4, 5, 6, 7. So to make it 8, I'll just pad it with a 0 at the beginning. This is what we were told here. It gets even better, uppercase A is different from lowercase a, which is why, if you notice, the equivalent binary for uppercase A is this, whereas the equivalent binary for lowercase a would be 97, right? Decimal number 97. So I'll come here and just convert the 97 to binary, and I will get this. By the way, if I convert this to hex, I'll get the same number I'm seeing here, the 61, right? This, yeah. It's just that I'm thinking it's a lot easier if you see this. But anyways, so there's that, right? And the same can be said for these other data formats like sound. So they told you that the sound is converted into a stream of ones and zeros in a very interesting way, because as I'm speaking to you, what's coming out of my mouth, right, is an analog signal. We were taught that the analog signal is going to be converted into digital format using something like your AC to DC converter or something, or a microphone in essence will convert it to the equivalent digital format. And all you're doing is you're just playing around with the waves, is it? I don't have an image here, but if you look at your sound wave, it turns out that you can generate discrete points, right? Those discrete points can then be normalized into, a stream of zeros and ones, ideally. Yeah. However, we are interested in I guess images, and to a certain extent, maybe I want to argue, if you think about what we're doing relative to animations here, maybe video. But what we know is that your I don't know if I talk about this, but I think I have. Yeah, I don't have this. Maybe not. Yeah. So there's your sound there, right? So you're using this to actually convert these points in blue into a 0, a 1, or something like that. So we were told that when you're dealing with video, what you can do is, given an input video, you can actually view that video as comprising a stream of images, right? Frames. So typically when you're generating video, like I am right now, so I'm recording this thing here using OBS, and behind the scenes, what OBS is doing is it's creating this. It's creating this file here. Yeah. When this file is created, or as this file is created, the application that I'm using to create this file implicitly will create it in such a way that it specifies how many images are stringed together in a given unit of time, in each second, ideally. And in fact, if you were to use a tool like this, I guess, you should be able to see the frame rate, ideally. I don't know if I'm, let's see here, it should be a frame rate somewhere. It's just, oh, it's not there. I don't know why I can't really see it here. Yeah, but the idea is, depending on the sort of tool that you're using, you should be able to see the the frame rate. I don't know if this is a preferred rate here. Could be it, maybe not, maybe, I don't know. And the idea behind your frame rate is quite simple, really, right? It specifies, I guess, the quality of the video itself. Usually when you're using things like your phone, for instance, if you're capturing motion picture using your phone, common frame rates that would be used would be things like, is it 30 frames per second or something? Whereas in games, you'd be working with much higher frame rates, like 60 frames per second, right? So you'd have, for 60 frames per second, you have a total of 60 images in each given second, ideally. Okay. Right. So, and again, this discussion we already had. If you remember, we're discussing the fact that as we are creating these 3D models, right? These triangles, for instance, in our model space, it turns out that ultimately, at the end of it all, we are interested in generating a pixel representation of what we're going to be drawing, right? And this brings us to a discussion of a difference between your so-called raster graphics and your vector graphics. I gave you scenarios of when exactly we tend to use these vector graphics. I think what was important was the fact that your typical vector graphics would actually be created using using mathematical functions or equations, ideally, whereas your raster graphics is actually made up of pixels. I don't know if you remember this. I gave an example by downloading from Google Slides. I think I downloaded a slide in SVG format, and I was actually able to open it up using a text editor, ideally. Something else maybe you may be interested in remembering is that you were introduced to a series of file formats, right? Is it vector graphic file formats and raster graphics file formats? It turns out that the more common formats that we tend to use when we're working with images would be your raster graphics, so your JPEG, for instance, and PNG. Whereas when you're dealing with vector graphics, you'll be working with things like EPS and SVG, right? Not that common. However, when it comes to presentation of information on the web, you will find SVG used often, as is the case with Wikipedia, for instance. Okay. Again, just an image showcasing the fact that you'd be using mathematical equations to actually draw your vector graphic, whereas your raster graphic will be constructed using a series of pixels. If you're interested in playing around with vector graphics or editing them, if you want, once you download it, what you can do is you can actually you probably want to find time and download tools like Inkscape. So the idea is simple. If I have an image like this or a slide like this, and I wish to maybe for some weird reason, I found myself wanting to, it's very strange here, wanting to edit images, right? I don't know if I should be saying this here, but there's a tool I was using to generate really aesthetically pleasing plots. It was a Google Docs plugin or something? However, after the trial period ended, they would actually the people behind the software would have a watermark in front, making it difficult for you to to actually integrate the let's say the graphic itself, let's say the plot or the chart, into a paper, right? And so what I was doing is I was exporting them as SVG, and then using an SVG editor to actually remove the watermark. It turns out that if you were to export this, if you export something that has a watermark as a JPEG or as a PNG, it's extremely difficult for you to remove that watermark, right? If not impossible or something like that. So what you can do is, there are online editors, but one of my personal favorite is a tool called Inkscape rather. And what Inkscape does actually, it allows you to literally peel out the layers that comprise of this this vector graphic in this particular case, and you'll be able to edit out these things. In this particular case, I would probably be able to easily edit out this text if I wanted to, and then re-export it as a derivative SVG file without the content that I don't want to appear here. Okay. Yeah. So in terms of what we are interested in today's lecture, we want to have a better understanding of how exactly this raster image is actually constructed. So it's a series of pixels, and if we were to use an example of this screenshot that I have in the slides, it turns out that the original image that I was using to construct these slides has a resolution or dimensions equivalent to 1365 by 612 pixels, right? So if I open up this image in any image viewer or a command line tool, for instance, you will notice that this thing will be able to show me the resolution of this, right? So if I was to say I wanted to resize here, I don't know if you can see this, but you notice that the current resolution of this image is 1000, right? 1365 pixels px by 612 pixels. Incidentally, the way this tool works is if I'm resizing, I can actually reduce the resolution of this image. And so the idea behind these numbers is simple, is it? What they're telling us is that, or what these numbers tell us is that this raster graphic actually comprises of 1000, so the width, right, from here all the way from the left to the right here, comprises of a total of 1365 pixels. So these small little dots, if I start zooming in into this image, what I'm saying is that from left to right, these pixels that you're seeing here, small little dots here, there are 1365 of them from left to right. And then in the height, you have a total of 612 little squares, okay? And so if you have, 1365 pixels in the width and 612 pixels in the height, then you can actually figure out the total number of dots that you have or that are being used to actually construct this scene that you're seeing here. Is it all you're doing is you're multiplying the 1635 by the 612, right? So you get a total of, in our case, you get a total of 835,380 pixels. Now I'm saying here per frame because if you think about this from the perspective of the game, the game itself, the Polyfit game itself, isn't really, it's not constructed using just still images. There's a bit of animation. And because there's a bit of animation, what we are saying is that every time we see some motion as we are playing the game, each frame associated with a second's worth of that animation comprises of 835,380 pixels or dots. Yeah. So the implications are simple here. What we are saying is, if we are using the more common frame rate utilized in gaming, for instance, would be looking at working with a 60 frames or FPS, 60 frames per second or 60 FPS for this particular game, meaning that in every second, you'd be working with an equivalent of 50.1 million pixels. So we are saying that the resolution is 1635 pixels by 612 pixels, right? And each image, so this is a resolution, right? Imagine the game itself as you are playing on, as I'm playing on my mobile device. The resolution I'm working with is 1635 by 612. However, if we just extract one frame, a frame which is a single image, we will have a total of 1635 multiplied by 612 pixels, right? So it's one frame is equal to this number of pixels. But remember, we are saying that for us to render this in a game, if we're working with 60 frames per second, what we are saying is that in one second, we have a total of 60 frames, is it? Well, what about, so this is 60 frames in 1 second. 1 second has 60 frames, meaning that and one frame, I've forgotten my direct proportion here. I guess it would be a lot easier if we do it from here, is it? 60 seconds, 60 frames is equal to 1 second. How about and this is the equivalent of 1 frame, is it? These are pixels. And we're interested in this, is it? We don't know how many pixels we have here, right? For 60 seconds. Right, so all we're doing is we're just multiplying this by this. I don't know if this is making sense. So in essence, the 50 million should be coming from here. Although it's about 60 million in this particular case, right? 1, 2, 3, 1, 2, 3. But that's an approximate value anyway. Right, so in every second, what the GPU has got to do is it's got to calculate the colors for each of these, not really 50.1 million, but each of these 60 million pixels ideally. Yeah? Remember, each individual pixel, if I zoom in here, each individual pixel on this frame here has a distinct color, right? So as you're playing the game, the GPU is constantly computing or recomputing the color associated with the pixel representation of the frame which is currently in focus, ideally. And incidentally, this is the reason why GPUs rose to prominence, is it? The fact that they're really, really good at doing these computations in parallel. So it's not really like these 60 million pixels will be processed one at a time, but they'll be done in parallel, right? On your GPU, ideally. Okay, so there's that. And then, so in terms of the pixel, right? I mean, in terms of the resolution, it becomes important for us to also talk about the aspect ratio. I'm sure you've seen a lot of this. Is it? They'll tell you that your phone? One of the marketing taglines will be like, your phone has an aspect ratio of, is it 16:9 or something, or 4:3 for older versions of phones or something like that. All you're doing really to come up with an aspect ratio is dividing the width with the height. It gives you an idea of how many pixels can actually be laid out in the width of your device and the height as well. In fact, this is so common, or this is so important, that you find it in a number of applications or a number of devices that we use on a day-to-day basis. So when I'm creating my slides, one of the things I've got to do is to ensure that I'm using the correct aspect ratio. And typically, this would have to be aligned with the device where these slides are going to be projected. In this particular case, it would be the projector. So if I'm using an older projector, what I would have to do is make sure that the aspect ratio I'm working with is not the modern 16:9, but rather the 4:3, right? Otherwise, you have a situation where you're projecting your slides and you know, they're not really aesthetically pleasing, and your images are scaled out and all those things. Incidentally, what I normally do is, if you notice the files I've been sharing, I'll create them in such a way that I'm reminding myself of the resolution I'm using. So in the event that I need to change this for an older version of the projector, I'll just recreate the slides, but have a 4:3 here at the end, right? That's your aspect ratio. Okay. Again, worth mentioning here that the more common aspect ratio for, I guess, a more modern Android phones would be a 20:9 aspect ratio. And then it's also important for us to talk about the memory cost associated with these pixels, right? Remember, we are when we're talking about this particular scene, we are assuming that we are working with standard RGB, meaning that the individual pixels that we have in our scene, like here, each individual box that you're seeing here is represented by a combination of 3 values, is it? R, G, and B, right? So red, green, and blue. And if you remember, we said that the common representation for this, or the bit depth that is normally used to represent this RGB format, would be a bit depth of about 8 bits, right? So the thing here is that the red component would be represented using a stream of 8 bits. The green component would be represented using a string of 8 bits. And then finally, the blue would be represented by a string of 8 bits as well. And if you remember your computer architecture, you begin to realize that if we have a situation where we have a pixel that is completely red, right? Would have something like this. Is it? Or more aptly put, it would be 255,0,0. Now, if you remember your computer architecture, right? They told you that putatively one byte is equal to 8 bits, right? And so if we are saying that each pixel on our scene here is represented by RGB, and each component of RGB has 8 bits, and 8 bits is equal to 1 byte. In essence, what we are saying is that each individual pixel is going to occupy, this is 8 bits, is it A? If this is 1 byte, this is another byte, and this is another byte. So in essence, what we're saying is that each pixel on the screen here, if you think about it from the perspective of memory cost, is going to occupy 3 bytes of memory space. In fact, you can also think about it from the perspective of how much space it's going to occupy, right? On your file system. So in essence, we are also saying that let me just get the file name here. We are also saying that we can actually approximate. We can approximate how much space. What the hell is this? How much space this file is going to occupy on file, is it? I'll remove the H here so that we see the number of bytes, right? So in this particular case, it's almost like we're saying we can get the theoretical amount of space required to store this image, which in this particular case is it 129,186 bytes? These are bytes here. Now, obviously, if we were to compute the I guess we can compute this. If we were to compute the theoretical size of, that's RGB, right, of this particular file, we're probably not going to get this, is it? Because we are saying that the total number of pixels in a single frame, right? Okay, one frame. I will just do this here. This is confusing, but I'll do this so that it's a lot easier for you guys to follow. These are pixels. These are frames. So one frame, like one image, has this number of pixels, is it? At the same time, we are saying, let's say pixel, byte. At the same time, we are saying that each pixel, each dot, 1 pixel, is equal to 3 bytes, right? So the question is, if each pixel, each one of these dots that you're seeing here, in the blown out scene here, right? If each one of these occupies 3 bytes, the question is, how many bytes is this going to occupy, right? X or something like that. So the theoretical size is actually supposed to be, 3 here, is supposed to be this multiplied by this. And I know what you're thinking. I say, well, but Lighton, if you're saying that if you're saying that this file is, the theoretical size of this file is supposed to be 180,111,600 bytes, why then is it that on file itself you have like 129,186 bytes? Well, we know, right, from computer systems that what actually happens is that there are some really fancy algorithms that are used in a JPEG format, for instance. So there's some compression behind the scenes, is it? We know that this wouldn't be sustainable if we're working with the actual the raw file without being compressed itself. If that is making sense. Maybe the other interesting thing worth mentioning here is that typically the theoretical size of the file. So if I was to get the original file in one of these like native formats or something, and measure it relative to, or compare it relative to the theoretical size, what you begin to notice is that the size that the file occupies on disk is going to be slightly larger than your computed theoretical size. And the reason is simple, right? Typically when you create a file, the metadata associated with the file, and there's usually a lot of metadata, is it? Besides the metadata, obviously, there's the way these files are created is you have the header information and all those things, but the header information plus the metadata, the auxiliary information that helps you define this file. In fact, this is a simplified version of the metadata associated with this file. It's usually much more, right? If you get your photo and if you capture an image using your photo and you run EXIF, you will notice that you have access to actually a lot more metadata than this. Now, the argument here is that this metadata, right, is embedded within the file itself. And so when you're checking the size of the file, it's a nice thing about this is the size that the pixels making up the image will occupy plus the space that the metadata and the header information is going to occupy, if that is making sense. Anyways, so there's that, right? So we begin to notice here that we can actually compute how large this frame is going to be, and in fact, hopefully you now begin to understand and appreciate why they'll tell you that a certain game needs you to have this minimum number of RAM, for instance, or the size, is it the free space that you need on your external drive, for instance, should be this, is it? Because usually, as you are rendering information on your game or something, you'd have to take into account how much memory is going to be used, right? And ideal, all of these things would be loaded into memory, if that makes sense. Right. So I hope this is beginning to remind us a bit more about what we did in computer architecture or something. Right. Again, so what we're saying is a pixel is nothing more than, this is for raster graphics, a pixel is just the smallest addressable unit on your screen. And one of the reasons why we work with pixels here is because of the design of the screens that we use, is it? it's a lot easier for us to view these images from that perspective. Okay. Again, just showcasing what some of the things we're going to be doing, especially as we are drawing these things on the screen. Remember, I said we're going to be using Pygame. One of the very first things we do is we specify the display size, right? So every time you see a code display underscore size is equal to 800, 600, what I'm essentially saying is, or what I'm telling Python or Pygame is that I would like to, I don't know where this thing is here, but what I'm telling Pygame is I would like to do this. I would like to draw a window, right? This is a window which is going to enable me lay from left to right 800 pixels, and then from top to bottom 600 pixels. So in essence, I'm drawing this triangle once it's rasterized, right? Using pixels that are going to be laid out, 800 of them left to right, and then 600 of them top to bottom, ideally. So we'll do this, right? Hopefully this will be very clear once we start doing this. Something else maybe worth mentioning here is, in as much as we're going to be focusing more on RGB, but we remember from computer systems, or if you don't remember, this is me telling you here, that there are usually different ways of representing colors, is it? One of the simplest ways of representing color on screen is just using plain old black and white. So what I did here is I just did a conversion of the original RGB formatted file from Polyfield, and then I converted it to monochrome, right? So monochrome is nothing more than a color that's essentially going to use just two different values, 0 or 1. So it's like black or white or something like that, right? In essence, you're working with one bit. So it as opposed to the RGB, which we are from discussing, which is going to help you represent your three different colors using 8-bit representation. Higher bit depths are possible, by the way. You can use 16-bit representation or 32-bit representation. But in this particular case, you're using 1-bit representation. And because you're using 1-bit representation, in essence, what you are saying is that you are just going to be representing this color like this, is it? I just call this monochrome. So it's like, because it's 1-bit representation, the number of possible colors are going to be 2 to the power 1. In this particular case, because we're using 8-bit representation, we're assuming 8-bit representation, the range of colors are going to be from 0 all the way up to, or rather, the range of colors are going to total 2 to the 8. Right? 2 to the power 8, which is 256. So if you're including 0, it would be 0 all the way up to 255. If you count all of those different values, you have a total of about 255, right? This is 8-bit representation. And then for monochrome, which is 1-bit representation, what you're saying is you're going to have a total of 2 to the 1, which is just 2 colors, right? Black or white, or something like that. Right, so 0 will be your black, and then 1 will be your white. It's quite simple, really. And obviously, you wouldn't want to do this if you're designing games. It has its place, I guess, if you're trying to create maybe some web app that is meant to illustrate vintage photos or something, right? To simulate how people used to see black and white or something. You do something like this, but it's not fun at all. Anyway, so that's 1-bit representation. But also, the other option is you can use grayscale. It's quite common as well. Again, if you look at the image here, it's slightly better than this one, but certainly not as good as this original RGB formatted image, right? With grayscale, what you're doing is, again, you typically be using 8-bit representation. However, you don't have these 3 color components like for RGB, is it? RGB, not RGC here. In other words, all you're doing is using 8-bit representation, you want to represent the different shades of gray. And it's like your 0 is going to be is going to be black, and then your 255 is going to be white. Anything in between is going to be a different variation of grayscale, if this is making sense. So I wish I had an application to showcase this. Maybe not, but I don't know, maybe not. I don't know if this is making sense, you people, right? Maybe just to demonstrate some of these things, I think I have an application, and I do encourage you to find time to probably play around with an application like ImageJ here. With ImageJ, which is an image processing application, what you can do when you open up an image is you can actually have a sense of the colors associated with the different pixels. So these dots that I was showcasing here, you see these things here? If I open up this file using ImageJ, not this, let me just see if I can. If I open up this file using ImageJ, I would have, oh wow, this is horrible. It starts with image, so IMG, and I want to make sure that I open the original, the original cropped image from Polyfield. If I open this up, yeah, and I hope I've opened it. I don't know if I have. I think I have. If I open it up, and what I'm going to do is just close this so that I can minimize all of these applications so that just remain with ImageJ here. Hopefully to be a lot more intuitive for you to understand. If I open up this image and I start, observe, if I don't know if you can see this here, but when I start moving my cursor, yeah, if I start moving my cursor on the screen, right in the, I don't know if you can see here, hope you can see my cursor here. If I start moving the cursor on the screen, you notice that the coordinates that are being rendered, is it? Like it's almost like this pixel here is at position 286, that's the x-axis. So I would count pixels, 256 of them from here, 1, 2, 3, all the way up to 286, comma, the y-coordinate, so from top here to the bottom, I would count the number of pixels and I would find it here. And then it's showing me the value, right? The value for, I don't know if you can see this on your phones here, but I know I can see it on my, I think you can actually. If you put it in landscape, you should be able to see this. Because I can see it on my phone. If you kind of zoom in here. The value, it's represented in two main ways, right? It's like comma separated decimal version and also hexadecimal representation. So the color, which is somewhere pointing at the sky here, is 136, 157, 210. 156, I don't know what this was here. Okay, I'll just get another one. It's like somewhere around here. 45, 123, 139. 139. So in other words, what they're telling me is that the color which is at that position is this, right? And with RGB, if this is a dotted version, then you can easily derive this color here, is it? Yeah, so that's that, right? In terms of how these pixels tend to be represented. You obviously wouldn't want to, for what we're doing, you wouldn't want to work with, certainly not with monochrome, which uses 1-bit representation. You won't really be able to do anything useful. I can't even think of an application of this. Maybe when you are when you're working with X-rays, perhaps. I think we've done this with X-rays. Your X-rays are typically not in color, if memory serves me right? It's like literally black and white. A classic use case scenario, or use case that can actually make use of this sort of this sort of color scheme here. Or is it Grayscale? I don't know. I think I've taken note here that context for this is medical images like X-ray. I'll have to check if X-rays use this or this, you know. Yeah, and then you have RGB. Again, just to try and showcase exactly how our scene would be modified if we tried to increase the intensity of the colors for either of the extreme ends of the RGB format. This is what you'd have, right? What I have going forward really is just maybe an explanation. I don't know if this would be necessary here, but I decided to include slides that tend to explain exactly how these colors are represented. This is because when you're talking about these images here on screen here, or when you're talking about the pixels that comprise of this image, in essence, implicitly, you're having a discussion centered around colors, right? So I have an explanation of how these different colors are represented and some of the computations I was just showcasing. In fact, I even went a step further to remind us that depending on the sort of use case where you're using these colors, in some instances you'd be using the hexadecimal representation of these different colors, whereas in some instances you'd be using the decimal representation of the color. So if you're using image manipulation software like GIMP or like Photoshop, for instance, you'd in all likelihood be using this, or a combination of both actually. Whereas when you're working on the web, you'd be using the decimal notation of this, but it's all the same. And then again, I have detailed slides that are essentially just showcasing exactly how rasterization works, right? So how these pixels are actually laid out on the screen. We've actually already discussed most of the things that are in the slides. The fact that for you to actually see the pixels associated with a given image, if it's a raster image, you'll have to zoom in, right? So that your image pixelates, and when it pixelates, you'll be able to have a sense of the individual pixels making up this this image like we have here, right? Again, I just had a visual representation of each of the pixels. I was just making things up here. I don't know if you guys have any specific questions. Maybe something else you may want to do as well is play around with hex editors, for instance. It'll give you an idea of the bits that actually make up your photo, your image. So what I did was I downloaded one of my favorite hex editors. I use Octeta. If I use Octeta to open again the image we've been using, which is this, and if I open it up, yeah, in Octeta, what Octeta does is by default, I don't know if you can see here, by default it uses because for it to make sense out of this, it has to be compact, is it? It's using hexadecimal representation, but you can change the view mode here and say, I want to leave the values in binary. And what you're seeing here is a binary representation of actually this image, right? So it has a stream of ones and zeros. I don't know if you can see here, these ones and zeros. In essence, some of these ones and zeros represents the pixels, is it? Because when you have an image like this, the way it's represented in memory is all of these stream of ones and zeros are concatenated together, is it? So it's a stream of ones and zeros, right? All the way up to the bottom. And you notice that it's quite lengthy here. I'm gonna pause here and find out if you guys have any questions about this. If not, the next time we meet, we shall start looking at the graphics pipeline, and hopefully a lot of these things that we've been discussing will probably make sense, is it? So when I start talking about aspect ratios, you will remember what this is all about. When I start talking about resolutions, you know what I'm talking about. When we start discussing the rasterization phase of the graphics pipeline, you will remember the discussion. In fact, even if we're not going to have a discussion centered around videos, you now should be able to know, as they taught you in computer architecture, is it? You should be able to know the implications of, let me just open this, the implications of this, what I'm about to show you right now. If you go on YouTube, the YouTube will tell you to say, when you're watching video, in some instances, if you're not paying attention in computer architecture, you don't really care what sort of resolution you're using. But if you're smart and if you're paying attention, you notice that YouTube will give you an option, is it, Under quality here, this is auto for me. It will tell you to say you can choose the resolution, right? It's like 144p, which is the lowest resolution, or 240p. In essence, what they're telling you is that if you downscale this to 140p, you are changing the resolution of the frames that are used to construct this footage. And this makes sense, right? Because, I don't know if it makes sense to you here, but this should make sense, right? Because because it has a bearing on the total number of pixels associated with the frame of the video you are watching. And because it has implications on the number of frames associated with the video you are watching, it is also related to the size of the frame that is going to be downloaded as you are watching this video. The size has implications on the bundles you have got to have in your account for you to watch this video. And if you're not smart like that, you'll be numbered amongst these people that don't know what's happening, and they'll be saying MTN or Airtel is stealing my bundles. I bought a 1 GB bundle and it's just finished within a minute or something. Well, you're watching the video in 1K or something, right? You probably want to downscale it. For me, really, something like 360p is usually sufficient. Even if I have an unlimited bundle, the quality is usually good enough. Anyways, I don't know if there are any thoughts or questions about this. If not, I guess we can leave it at that. Any thoughts or questions? No? Yes? And people have left. I don't know. So do you have some code tutorial sheets or some sorts we can practice in this NumPy? Yes, so I mentioned that once we are done discussing the graphics pipeline, I think the next lecture series we involve just a crash course introduction to the packages we're going to be using, and I will share examples and lab problem sets actually to help you to help you practice. And then there's a question here: what are we supposed to use to draw the triangle? Well, we'll be using PyOpenGL to do this. And again, I'll showcase examples in class. It's not as hard as it may look here, probably because you haven't done it before. But you'll notice that it's quite easy actually. And then there's a question here says, is it a standard that one frame is this? No, it actually differs. You see, the number that you've computed here, this number is dependent on the resolution. Here's another example I have before we part ways here. If you look at some of these images, and I'm glad you asked this question, right? This image here, I have two images. The one we are using from Polyfield, yeah? This is a file name. The other image that I showcased as an example, I told you that I obsess a lot about cultural heritage preservation. This image here. This was this image here was captured using my phone, and this is a file name. If I check the resolutions for these images, yeah, observe. If I check the resolution for the Polyfield game, oh no, not this. I want the original scene file, which is this. This is what we've been using as an example. This is what we've been using as an example. So I want to open this here. This is a file name, is it? If I just use sorry about that. If I just use identify here, notice the resolution for the image that has been extracted from Polyfield, and I just got a screenshot and I cropped it, right? This is not the actual resolution here. So it's 1365 by 612. However, the resolution for the image from my phone, which is this, is like 4000 by 3000. In fact, it looks smaller here, right? It looks smaller here because by default, the way my application works, the way GwenView works is it kind of resizes the image so that it fits the screen. If you notice here, I've told it to just fit the screen. If I zoom into 100, this is more or less like the way it's supposed to originally look like, right? I don't know about this guy, he's pinning his hair. But so to answer your question, for the example we are looking at, which is 1635 times 615, we have this number of pixels. This is from Polyfield. However, if I look at my OnePlus, 1 plus 9R. When the default configuration on my phone is such that, you notice here, I've captured, and I think this was, I don't know if this was like in portrait or I think it was in landscape, is it? Because the width is much larger than the height. If it was the opposite, then the photo was captured, would have been captured in portrait. I don't know, those of you that capture videos in vertical mode, right? Vertical videos and stuff. But for this particular example, the total number of pixels would be 4,000 multiplied by 3,000.
Dr. Lighton.
Yes, hi.
Sorry, sir, we have another class.
Oh, okay. That's fine. I was answering a question. That's fine. Let me just answer the last question here, sir.
All right, thank you.
Notes, and can we treat this course as a basis for graphic designing? Not really. I mean, when you're talking about graphic designing, right? One of the things you'd be doing is people would be introducing you to tools like graphic designing was supposed to have been introduced to you in that elementary course. I don't know the course you did. Is it computer IT essentials or something like that? Second year course. So you'd be working with tools like Inkscape, right? If you're looking at graphic designing, or GIMP, right? GIMP is like your open source kind of alternative to Photoshop or something. So the answer is no, really. We are looking at primitives that most of these things actually abstracted away from you when you're dealing with graphic designing, wherever that was. All right. Okay. The last thing is we have class. Good luck with your class. Thank you very much, everybody, and see you when you see me again. A reminder that our class next week is going to be virtual again. Thanks. Bye.